We can use the concept of effective nuclear charge to think about the trends in atoms, sizes, and other properties of the atoms. We're going to look right now at the size of neutral atoms and think about the periodic trends or the trends that we can see from one atom to another atom in the periodic table. But first we need to define what we mean by the size of an atom. So if I take two atoms and I try to put them as close together as I possibly can, eventually what's going to happen is that the valence electrons in this atom and the valence electrons in this atom are going to get so close to one another that they're going to repel one another, and I'm not going to be able to push those atoms any closer together than a particular distance. So if I look at the distance, so if I push them as close as I possibly can so that the electron-electron repulsion makes it so I can't push them any closer together, and I look at the distance between the nuclei, that is going to be equal to one radius plus another radius, so that's going to be equal to the diameter of one of these atoms. So this distance here is equal to the distance across here. So the diameter of an atom can be defined by the distance of closest approach to another atom of the same kind. So if we look at the trend, if we go across a row in a periodic table or down a column in the periodic table, we can think about how the size of these atoms might be affected. Notice that the size of the atoms depends on where these valence electrons are. So if the valence electrons are closer into the nucleus, then I'm going to be able to get those two nuclei closer together. If the valence electrons are further away from the nucleus, then I'm not going to be able to get those atoms as close together, and so the size is going to be larger. So in another sense, then, the size of the atom has to do also with how far away the valence electrons are from the nucleus. Another way to think about the size of the atom is to think about where the most probable distance is for those valence electrons. And so if the electrons are in the valence electrons are in a higher end shell, then the most probable distance is going to be further away. And if it's further away from the nucleus, then I'm not going to be able to get the two atoms as close together, and that's going to be a larger atom. So larger atoms, higher end level, smaller atoms, smaller end level, electrons closer into the nucleus. So remember that we said that the effective nuclear charge for the valence electrons is going to increase as we go across a period or across a row, and it's going to decrease as we go down a column, which means it's going to increase as we go up a column. And so that means that overall, the effective nuclear charge is going to increase in this diagonal fashion. The stronger the effective nuclear charge for those valence electrons, the more tightly they will be pulled in towards the nucleus. And so the smaller those atoms are going to be. So as the effective nuclear charge increases, the valence electrons are pulled more tightly towards the nucleus, and so the size of the atoms is going to decrease as the effective nuclear charge increases. And so we have up here our smallest atoms, and down here we have our largest atoms. So size decreases as Z effective increases.